This video will introduce the basic concepts underlying thermodynamics, such as temperature and kinetic theory. Some, but not all, of the concepts should be a review from your previous chemistry course. Modern atomic theory states that matter is made of atoms. In all matter, including solids, these atoms are in continuous motion. In a gas, the atoms move about randomly throughout the entire material, often colliding with other atoms or the walls of the container. In a solid, the atoms do actually move, but their movement is more of a vibration. The attractive forces between the atoms are strong enough that the atoms or molecules move only slightly, about relatively fixed positions, often in a pattern known as a crystal lattice. The idea that atoms are in continuous motion is known as kinetic theory. As you may recall, kinetic is Greek for moving. In everyday life, temperature is defined as a measure of how hot or cold a substance is. Temperature is measured with a thermometer based on the principle of heat expansion. When the temperature of a material increases, the material tends to expand. The glass exterior of a thermometer expands when it's heated, but at the same time, the substance inside, which is alcohol or mercury, expands to a larger extent, so the level of the alcohol or mercury rises, indicating a higher temperature reading. This idea will be developed further shortly. 3 temperature scales can be used to define temperatures: Celsius, Fahrenheit, and Kelvin. We will next take a look at these 3 scales, as well as see how one scale can be converted to another. Temperatures can be converted from one scale to another. To convert from degrees Fahrenheit to degrees Celsius, we must take the temperature in degrees Fahrenheit, subtract 32, and then multiply that quantity by 5/9. To do the opposite, change a temperature from degrees Celsius to degrees Fahrenheit, we have to take the temperature in degrees Celsius, multiply it by 9/5, and then add 32 to that quantity. And finally, to convert from degrees Celsius to Kelvin, we take the temperature in degrees Celsius and add 273, or to be more precise, 273.15. You will not have to memorize the first 2 equations, but you must memorize the third. This will be used throughout the entire thermodynamics unit. As you can see, each temperature on one scale corresponds to temperatures on the other 2 scales. For example, water freezes at 0 degrees Celsius, which is 32 degrees Fahrenheit, or 270 Kelvin. The boiling point is 100 degrees Celsius, 212 degrees Fahrenheit, or 373 Kelvin. The lowest temperature is negative 460 degrees Fahrenheit, which is negative 273 degrees Celsius, or 0 K, or 0 Kelvin, on the Kelvin scale. 0 Kelvin is defined as absolute zero. Supposedly, this is the lowest possible temperature. At absolute zero, molecular motion is said to cease. Let's try a few problems. Normal body temperature is 98.6 degrees Fahrenheit. What is the temperature on the Celsius and Kelvin scales? So notice, our starting temperature is in degrees Fahrenheit, and we'd like to convert it to Celsius and Kelvin. So we'll start with converting that temperature to degrees Celsius. Using the equation, we will take 98.6 degrees Fahrenheit and plug it in for temperature. We'll subtract 32 from 90.6 and then multiply that entire quantity by 5/9. Plugging into the equation, we get 37 degrees Celsius. Now, to convert this to a Kelvin temperature, we must use the equation temperature in Kelvin is equal to temperature in degrees Celsius plus 273.15. Plugging into the equation and solving, we get a temperature of 310.15 Kelvin. You can rewind to the last diagram to see how these temperatures correspond to each other. For our next problem, the moon at its coldest is negative 173 degrees Celsius. What is this temperature on the Fahrenheit and Kelvin scales? So our starting temperature is in degrees Celsius, and we need to convert it to Fahrenheit first. So we take the temperature in degrees Celsius, multiply it by 9/5, and then add 32. Plugging into the equation, we get a temperature in degrees Fahrenheit to be 279.4. We then are asked to determine the Kelvin temperature. Remember, to find the Kelvin temperature, we take the temperature in degrees Celsius and add 273.15. Don't just assume that the temperature we just found is what we'll plug into the Kelvin formula. It must be temperature in degrees Celsius. So we plug in negative 173 degrees Celsius, add to it 273.15, and we find the Kelvin temperature to be 100.15 Kelvin. You should be familiar with the concept that if two objects at different temperatures are placed in thermal contact with each other, meaning that heat can flow between them, they will eventually reach the same temperature. The two objects are said to be in a state of thermal equilibrium, meaning that they are at the same temperature. This is because the hotter object cools down slightly, the cooler object warms up, and they will finally reach the same temperature or thermal equilibrium. For example, if you leave a spoon in a bowl of hot soup, the spoon and soup will eventually reach the same temperature or thermal equilibrium. A fundamental law of thermodynamics approaches this idea from a slightly different perspective. Consider three objects, A, B, and C. A and C are in thermal contact, and B and C are in thermal contact, meaning that heat can flow from one object to another. However, A and B are not in thermal contact with each other, meaning that no heat can flow strictly between the two of them, A and B. Because C is in contact with A, they will eventually reach thermal equilibrium. But C is also in contact with B, meaning that they will ultimately have to reach the same temperature as well, reach thermal equilibrium. Thus, A and B will essentially reach thermal equilibrium, even though they aren't in direct thermal contact. This defines the zeroth law of thermodynamics, which states that if two systems not in direct thermal contact are in thermal equilibrium with a third system, then they are essentially in thermal equilibrium together. This law has an unusual name because it wasn't until after the first and second laws of thermodynamics had been worked out that scientists realized this postulate needed to be stated first. Most substances expand when heated and contract when cooled. However, the amount of expansion or contraction varies depending on the material, as we saw from the thermometer example. The glass expanded, but the mercury or alcohol inside the thermometer expanded more. But how do we determine exactly how much an object expands or contracts? We will first analyze linear expansion. Let's consider a straight rod with given length L0. When this object is heated, it will expand. Experiments indicate that the change in length, or the amount of expansion of a solid material, is directly related to the initial length, L0, the change in temperature, delta T, and a constant, alpha, which is known as the coefficient of linear expansion, which is a material-dependent property. Each material has its own coefficient of linear expansion. These values can be found on page 358 of your textbook. For example, the coefficient value for glass is 9 times 10 to the negative 6 degrees Celsius to the minus 1, or 1 over degrees Celsius. The coefficient value for Pyrex is 3 times 10 to the negative 6 degrees Celsius to the minus 1. This is why baking pans are made out of Pyrex and not glass. If glass were used, more expansion would take place because the coefficient of expansion for glass is higher. Pyrex, with a lower coefficient of expansion, will still expand, but not to the same extent that glass expands. There are many examples of linear expansion in everyday life. For example, on highways, large sections of concrete are separated by a very small gap with metal teeth, as shown. As the concrete and metal heat up, they expand and the gap closes. But as the temperature decreases, the materials contract, causing the gap to widen. These expansion joints allow for the expansion and contraction of the bridge caused by the changes in temperature. If these expansion joints weren't in place, the bridge would expand and contract against itself and crumble. Next time you're on a bridge, listen to the sound of the tires going over each expansion joint. If it's a hot day, most likely the sound will be almost undetectable. But on a cool, cloudy day, the gap will be very noticeable because those sections are contracting and the gap is becoming larger. A similar relationship can be used to determine the change in volume of an object as it undergoes a temperature change. Let's consider a cube with an initial volume V0. The change in volume, delta V, is directly proportional to its initial volume, V0, the change in temperature, delta T, and beta, the coefficient of volume expansion. Again, these values can be found on page 358. You may notice, when looking at the table on page 358, that the value of beta is usually right around 3 times the value of alpha. This is by no accident. Let's try a couple practice problems. Steel railroad tracks laid at a temperature of 5 degrees Celsius have a length of 12 meters. If the temperature can reach 55 degrees Celsius, what size expansion gaps are needed? The coefficient of linear expansion for steel is given as 12 times 10 to the negative 6 degrees Celsius to the minus 1. To calculate the change in length, we use delta L equals alpha L naught delta T. Plugging into the equation the coefficient value for alpha, the initial length value, L naught, which is 12 meters, and the change in temperature, which is the final temperature minus the initial temperature, or 55 degrees Celsius minus 5 degrees Celsius, we get a value of 0.0072 meters. So this is the size of the expansion gap needed to allow the steel railroad tracks to actually expand. As you can see in the diagram, railroad tracks are laid keeping this in mind, that they will, because they're heated, expand and contract if they're cool. So there must be these expansion gaps in place to allow that expansion to take place. Next problem. A brass cup filled to the brim with 240 milliliters of water at 4 degrees Celsius is heated to 95 degrees Celsius. How much water will overflow if the beta for brass is 56 times 10 to the negative 6 degrees Celsius to the minus 1, and the beta for H2O is 210 times 10 to the negative 6 degrees Celsius to the minus 1. To find the amount of water that overflows, we can first figure out the change in volume of the water as it's heated. And we do that by taking the beta value for water, multiplying it by the initial volume of water, and by the change in temperature. But not only is the water expanding when it's heated, but the brass cup is also expanding when heated. And we can determine how much the brass cup expands as well. The delta V of brass is equal to beta of brass times the initial volume of brass times the change in temperature of the brass. The difference of these two amounts will give us the overflow amount. So to find the difference between the two, we can pull out the betas. So we have the beta for water minus the beta for brass, and then multiply that quantity by V naught and delta T, because the volumes are the same and the changes in temperature are the same. Plugging in our values, as shown, we get a difference to be 3.36 milliliters. So 3.36 milliliters of water will overflow as a result of the expansion of both of these objects. Here's an interesting thought question for you to consider. Do holes expand or contract? If you heat a thin circular ring, example, does the ring's hole get larger or smaller? You might guess that the metal expands into the hole, making the hole smaller. However, if we imagine the ring is solid like a coin, the entire disc would get larger. When the metal expands, the material inside the circle will expand along with the rest of the metal, so the hole actually gets larger. You could also imagine that we cut the ring and hurl it or straighten it out. The metal, when heated, will expand linearly. If we allow the metal to expand and then reconnect the ends to create the ring, the hole inside will have a larger diameter. You may have wondered why, in the previous example, we used 240 milliliters as the volume of the fluid inside as well as the volume of the container. When the container expands, it doesn't expand inward, thus decreasing the volume of the container. It expands outward. Another practical application of this outward expansion is when you're trying to remove lid from a jar that is tightly sealed. You can run the jar and the lid under hot water. Both materials will expand, but they will expand at different rates. The metal lid will actually expand at a greater rate than the glass jar. But what is important to recognize is that the lid won't expand inward, creating a tighter seal. The lid will expand outward, thus making it easier to loosen the lid. We have just looked at how materials can expand or contract when they're heated or cooled. But gases behave differently than solids or liquids. It is true that when temperature increases, a gas can increase its volume or expand if the container allows it to do so. But in addition, the volume of a gas depends on the pressure. It is therefore more valuable to determine a relationship between the volume, pressure, and temperature. Several experiments have shown relationships between each of these quantities. Boyle's law indicates that the volume of a gas is inversely proportional to its pressure when the temperature is held constant. Charles' law shows that the volume of a gas is directly proportional to its absolute temperature when the pressure is held constant. Finally, Gay-Lussac's law indicates that at constant volume, the absolute pressure of a gas is directly proportional to the absolute temperature. The three laws can be combined into a single, more general relation called the ideal gas law, which is written as P times V equals N times R times T, or PV equals nRT. P is the absolute pressure, V is the volume, lowercase n is number of moles, T is the temperature, the absolute temperature, and finally R is known as the universal gas constant, which has a few different values. The first value, which is the most common, is 8.314 joules per mole Kelvin. There's also another value for R, which is 0.0821. However, the reason there's a different value is because the units are different. The units for this R are liter atmospheres per mole Kelvin. It is important to note that when using the ideal gas law, all temperatures must be absolute temperatures, measured in Kelvin, and all pressures must be absolute pressures, not gauge pressures. Another version that is often used is more of a comparison between two different states. We can rearrange the ideal gas law formula to get N and R on one side. So we find P times V divided by T is equal to N times R. N is the number of moles, which is constant, and R, the universal gas constant, is also constant. So therefore, N times R is constant, or PV over T is constant too. If PV over T is constant, then we can set it equal to another PV over T for a different state. So we see that P1 V1 over T1, that's one state, is equal to P2 V2 over T2. That's the second state. Because NR is a constant, and because PV over T is constant. One final version of the ideal gas law uses number of molecules, capital N, instead of number of moles, lowercase n. In order to do this, we have to use Avogadro's number. Recall from chemistry that the number of moles is equal to the number of molecules divided by the number of molecules per mole. We can see that the number of molecules actually cancels out of both the top and the bottom, and we'll be left with 1 over per moles. But a per mole is a 1 over a mole. So we have 1 over moles, which will give us just the number of moles. This can also be shown in symbols. Lowercase n is equal to capital N over Na, and Na is Avogadro's number. But recall, from the ideal gas law, PV equals nRT, n being lowercase n, the number of moles. We can take the equation for number of moles and plug it into the ideal gas law formula. So we get PV equals number of molecules over Avogadro's number, that whole quantity times R times T. But note it, R is a constant, and Avogadro's number is a constant. If we have R divided by Avogadro's number, that's going to give us a new constant, which we give the symbol lowercase k, which is called the Boltzmann's constant, which has a value of 1.38 times 10 to the minus 23rd joules per Kelvin. We can then replace the R over Avogadro's number by K, and we find the new ideal gas law formula is PV equals capital N KT. Let's take a look at a few practice problems. Determine the volume of 3 moles of any gas, assuming it behaves like an ideal gas at their temperature and pressure. The formula for the ideal gas law is PV equals nRT. We can plug in the pressure at STP, which is 1 atmosphere, or 1 times 10 to the 5th pascals. V is what we're solving for. N is the number of moles, 3 moles. R is the universal gas constant, which in this case we're going to use the joule value. So 8.314 joules per mole Kelvin, and then multiplied by 273 Kelvin, because the standard temperature is 0 degrees Celsius, or 273 Kelvin. Plugging in and solving for the volume. Find the volume to be 0.06 meters cubed. You may also convert this to liters, and the conversion factor for liters is 1 liter is equal to 1 times 10 to the minus 3 meters cubed. And we can determine the value in liters to be 60 liters. 3 moles of any gas turns out to be 60 liters of volume. For our next problem, let's consider an ideal gas in a container called a piston. This is an ideal gas that has a volume of 3 liters, temperature of 20 degrees Celsius, and a pressure of 1 atmosphere. It undergoes a few changes, and its volume changes to 1 liter, temperature turns to 40 degrees Celsius, and P2, the pressure, is not given. Part A asks us, what is the value of P2? And for B, the piston and the handle are very light. The area of the piston is 0.02 meters squared. What is the force provided by the gas required to keep the frictionless piston in place and keep the volume equal to 1 liter? as it is in the second case. Because we are comparing two states of the same gas, we can use the equation P1V1 over T1 equals P2V2 over T2. We plug in the initial pressure, 1 atmosphere, the initial volume, 3 liters, and the initial temperature. But notice this temperature has to be in Kelvin because it's an absolute temperature. So we have 293 Kelvin. And we set that whole quantity equal to P2 because it's unknown, V2, which is 1 liter, and then divide by T2, the absolute or Kelvin temperature, which is 313 Kelvin. Again, I'll make the statement. This temperature has to be in Kelvin in this equation. Rearranging and solving for P2, we find the pressure to be 3.2 atmospheres. So that is the answer to part A. Part B asks us to find the force that keeps this volume of 1 liter. Well, we know force is equal to pressure times area from our fluids unit. Plugging in the pressure as the pressure difference between the inside and the outside. The inside pressure is 3.2 atmospheres, or converting to pascals, 3.2 times 10 to the 5th pascals. And subtracting from that the outside pressure, which is 1 atmosphere, 1 times 10 to the 5th pascals. And taking that pressure difference and multiplying it by 0.02 meters squared, the area, we find the force to be 4,400 newtons. Recall that the analysis of matter in terms of atoms in continuous random motion is called kinetic theory. We must make a few assumptions about the molecules in a gas to reflect a simple view of a gas. The first assumption is that there is a large number of molecules, each with a certain mass, moving in random directions with a variety of speeds. So lots of molecules, different directions, and tons of different speeds. Second, we must assume that molecules are on average very far apart from one another compared to the actual size of the molecules. 3, we must also assume that the molecules interact with each other only when they collide. There are no weak attractive forces, or we're not considering those weak attractive forces between the molecules when they're moving about through the material. So they interact with each other only when they collide. And finally, the collisions that take place with other molecules or with the walls are assumed to be perfectly elastic collisions, meaning that there is no total kinetic energy lost when these collisions take place. Recall from our energy unit that kinetic energy is calculated using the formula 1/2 mv squared. But if we're looking at the molecules, kinetic energy of the molecules in a gas, each molecule is moving with its own speed and therefore has its own kinetic energy. But we're going to look at the gas as a whole, and so we're going to calculate the average kinetic energy of the molecules using the average speed of these molecules. So, to determine the average kinetic energy, we use the formula 1/2 mv average squared. But it can also be shown that the average kinetic energy of a gas can be calculated using the formula 3/2 kT, where K is Boltzmann's constant from before, and T is the absolute temperature. What does this mean? Well, this says the average translational kinetic energy of molecules in random motion in an ideal gas is directly proportional to the absolute temperature of the gas. In simpler terms, the higher the temperature of a gas, the faster the molecules are moving on average. And the opposite is true as well. The lower the temperature, the slower the molecules are moving on average. Now recall from before, we said that the lowest possible temperature is 0K, or absolute zero. Now, absolute zero is an extremely low temperature, so if we're continuing to lower the temperature, the molecules are moving slower and slower. So as we get to this lowest possible temperature, the motion of the molecules is becoming so slow that it's said to stop. So absolute zero is really defined as the point at which the molecules stop moving. Now, to determine exactly how fast the molecules are moving, we can use the two equations for average translational kinetic energy. We can set the two equations equal to each other, and for the speed. So we have 1/2 mv average squared is equal to 3/2 kT. Now, it is important to notice in this equation that m, in this case, is the mass of a single molecule. So we're looking at the speed and the kinetic energy of a single molecule, not the entire gas. So m is the mass of a single molecule. Now rearrange this equation to solve for V average. We divide both sides by 1/2 m, so we get V average squared is equal to 3/2 kT over 1/2 m. Now to get V average by itself, we have to take the square root of both sides, and notice when we take the square root of a squared term, they cancel each other out, and so we're left with the average speed equals the square root of 3/2 kT over 1/2 m. This is known as the root mean squared speed. The root mean squared speed, because we're taking the root of the mean squared. Now we can simplify this equation a little bit further. We have 3/2 on top and we have 1/2 on the bottom. The halves can cancel out, and we'll be left with the square root of 3 kT divided by m. And again, this is known as the root mean squared speed, so we give this symbol VRMS, or the RMS root mean squared speed. Again, it's important to see in this final equation, m is equal to the mass of a single molecule and not the mass of the entire gas. So when we're finding the speed of the molecule, let's take a look at our first example. 0.2 moles of oxygen gas at 300 kilopascals has a volume of 0.005 meters cubed. A. What is the average translational kinetic energy? And B. What is the total translational kinetic energy? For A, to find the average kinetic energy, we could use the formula 1/2 mv squared, but we don't have mass and we don't have the speed, so we can use the alternate equation, 3/2 kT. But notice we are not specifically given the temperature. However, we have pressure and volume. So, we can use the equation for the ideal gas law, which is PV equals nRT. Plug in pressure. Notice the pressure is changed to pascals, not kilopascals. We have the volume in meters cubed. N is the number of moles, 0.2, and we plug in the universal gas constant, R, 8.314 joules per mole Kelvin. Now, we're solving for the temperature T, so plugging in and rearranging, we find the temperature to be 903 Kelvin. So now we can plug that temperature into our average kinetic energy formula, 3/2 kT, and we find the average kinetic energy of the molecules to be 1.87 times 10 to the negative 20 joules. Part Part B asks us to find the total translational kinetic energy of the entire gas. Now, the average translational kinetic energy just refers to the kinetic energy of a single molecule, or the average of a single molecule. So to find the total kinetic energy, we have to take the average kinetic energy and multiply it by capital N, the number of molecules. We aren't specifically given the number of molecules, but we can find it if we know the number of moles and Avogadro's number. So capital N, the number of molecules, equals lowercase n, number of moles, times Avogadro's number. So we take 0.2, our number of moles, and multiply by Avogadro's number, 6.02 times 10 to the 23rd, plugging that in for our number of molecules, and multiplying by the average kinetic energy of these molecules, we find the total kinetic energy to be 22,050 joules. There is an alternate solution to Part B. We did say that the total kinetic energy is equal to the average kinetic energy times the number of molecules. But if we plug in the equation for average kinetic energy, 3 halves kT, then we find that the kinetic energy total is equal to 3 halves kT times capital N. But if we lump the K and the N together, the product of capital N times K is actually equal to lowercase n times R. So we can replace the capital N K by lowercase n R. And so we have the total kinetic energy is equal to nRT. But by the ideal gas law, PV is equal to nRT. So what we can do, instead of finding the temperature first, we can just take out the nRT and put in P times V, because PV is the same as nRT. So our new formula for the total kinetic energy is equal to 3 halves P times V. Plugging in the pressure, 300,000 pascals, and the volume, 0.005 meters cubed, we find the total kinetic energy to be 22,050 joules. Same answer, just a slightly different solution. For our next problem, we are asked, what is the root mean square speed of 2.5 moles of hydrogen gas at 4 atmospheres and 300 Kelvin? Note that the molar mass of hydrogen is 2 grams per mole. Recall from our derivation, the root mean square speed equation is 3 halves kT over n. But recall that n is the mass of a single molecule, so we can't just use the molar mass. It's the mass of a single molecule. So we have to find that. If the molar mass is 2 grams per mole, or 0.002 kilograms per mole, we can divide that number by Avogadro's number, 6.02 times 10 to the 23rd molecules per mole. Our moles will cancel out, and we'll be left with the mass per molecule, or the mass of a single molecule. And then we can plug that value in for, so we have the root mean squared speed is equal to the square root of 3, K, which is 1.38 times 10 to the negative 23rd joules per Kelvin, and plugging in the temperature, 300 Kelvin, dividing that whole quantity by 3.32 times 10 to the negative 27 kilograms per mole, that's what we just found, and solving for root mean square speed, we get 1,934 meters per second. So that is the average speed of the molecules, the root mean squared speed of the molecules. You can go about determining the root mean squared speed in another way as well. Our derived formula for root mean squared speed is equal to the square root of 3 kT over n. But Remember, K, Boltzmann's constant, is the universal gas constant, R, divided by Avogadro's number. We can plug in R over Na for K, and our formula will look like this. Now remember, we said this M in this equation is the mass per single molecule, the mass of a single molecule. But maybe we don't know the mass of a single molecule. But M times Na is equal to the mass per molecule times the molecules per moles. So M is the mass per single molecule, and multiply that by Avogadro's number, which is number of molecules per moles. The molecules will cancel each other out, and we'll be left with M times Na is equal to a capital M, which is the molar mass, or the mass per number of moles. So because we have M times Na, the product of these two values in the denominator, we can replace them with capital M, the molar mass. And so we get the root mean squared speed equation to be the square root of 3RT over capital M, where in this case the capital M is the mass per mole, or the molar mass. And plugging in for our root mean squared speed, we get, again, 1,134 meters per second. Same answer, but a slightly different approach.